indivisibly, because meaning that it couldn't be divided, indivisibly small atoms that he called atomos. Okay? He called them atomos. That was the first name for the atom, the atomos. It's this tiny, hard, solid, and that's why I'm shading it in, because we're going to get to different models. Okay? And that's part of our quiz and test. This hard, solid sphere that he called atomos, Democritus. Okay? It says here, meaning, this word atomos, meaning not to be, quote unquote, cut up into smaller pieces, or we cannot divide it. So the word atomos means that it cannot be cut up anymore. It's like a solid little BB. Like, imagine a metal BB. That's what he thought atoms were. And he says they were so tiny that we can't even see it. Well, he knew that part was correct. Like, if you had an atom in your hand, it's right there, but you just can't. But as you continue to have more atoms and more atoms and more atoms, then you're able to see that solid material. You just had to have these thousands and millions of them. Okay? He also believed that each atom was made up of a homogeneous, we know that word now. That's the reason why we do things in certain orders, so we have these vocab words. Homogeneous materials. So if it was, for an example, gold atom, then all of them were exactly the same. So he had some idea, and he was correct on some stuff, but some stuff he wasn't correct.
He kind of was guessing.
He was guessing. He was guessing at the time.
He made pretty good logic.
He made some pretty good guess, some pretty good hypothesis. But around 1766 to 1844, can you imagine? Look, we're talking about 430 BC. Whoa, I'm talking long time ago. Long time ago. It took years to have passed before John Dalton said, you know what? Okay, we're going with Democritus, and I think he's a little bit incorrect. Okay, so John Dalton had the nerves. Here's a picture of him. I don't know about you, but I like to see a little bit. I kind of changed my notes up a few years back because I was like, you know what? For us to see these names, I needed to see a picture to go with it. So here's a picture of John Dalton. Okay? So it says here, John Dalton says that he revised Democritus' theory. He said, you know what? Yeah, you're kind of right, you're kind of wrong. John Dalton, back in 1803-ish, he became known as the father of modern atomic theory. And I don't know about you, but in 1803, we're considering that to be modern, okay? Compared to right now, we're 2025. But in 1803-ish, Dalton's theory started becoming, he got the title of father of modern atomic theory. Bless his heart, we don't even use it. His theory got swapped out about 3 more times after he came up with this theory. We don't even use it anymore. But let's look at letter A. It says here, all matter is composed of tiny individual particles called, where did my words go? Called atoms. It says over here, all atoms of an element are identical. Then, atoms cannot be created, divided, or destroyed. Right, exactly. Atoms of different elements combine chemically to form compounds. Oh. Example, like H2O. Okay, so now this is John Dalton's theory. John Dalton, back in 1803-ish, gets this title of, the father of modern atomic theory. Now, let's go back and look at his suggestions. This is what he said. All matter is comprised of these tiny individual particles called atoms. So we would go from the word atomos into atoms. So that means that if John Dalton believes this in his gut, his hardcore gut, then that means that he also believes that we're the solid sphere. So he's taking Democritus' suggestions and he says, you know what? I believe that part of you, Democritus. I believe that we are these tiny, if it's a chunk of gold, a chunk of coal, a chunk of iodine, which would be liquid, a chunk of sodium, okay, which would be a solid. If we had these chunk of these elements from the periodic table, he said that all matter is composed of these tiny indivisible particles called atoms. Let's take this word atomos and let's call it atoms, he says. We're going to twist it to an 1803-ish words. Is that true or is that false? I'm going to go with a different color pen. That is completely false. I agree with you 100%. We haven't even had this unit yet, and you're already correct. That's false, Miss Munson, because it's not this hard, solid sphere. It's this thing that has a gravitational pull between the electrons, protons, and neutrons that are a spherical kind of shape-ish. So no, Miss Munson, that's false. I agree with you. Let's look at letter B. John Dalton says all atoms, and remember, in his gut, A, B, C, D, E. Oh, I forgot E. We'll go back to E in a moment. B says all atoms of an element are identical. He says that if you're gold, you are gold. Now pause for a moment. I said, hey, atoms have been here on this earth since earth was created. Okay? And I don't know about you, but I've been here on this earth since I was created back in a long time ago. Okay? And so since I've been here on this earth, I have aged. Guess what? Atoms age too. Can you imagine the atom of those dinosaur times? They're still around, these same atoms? Well, true story, they are still around. They don't stay the same and are identical. They actually, quote unquote, age, and they become what we call isotopes. So that's actually false. Again, how do we know that he's false? Because of new technology. New technology is helping us identify some things that are wrong that we believed in. Letter C, John Dalton said, atoms cannot be created, divided, or destroyed. And I heard that, Ms. Munson, he's kind of wrong. And I agree that this is a false statement too. Why? They could, how? Thank you. Nuclear fission. Some of us call this a nuclear bomb that we don't want to go off here on Earth because we know that when a nuclear bomb or nuclear fission as well as fusion, fission, we rip it apart. Fusion, we fuse it together. Can occur. And when that happens, crazy amount of energy is released. Give it to me.
Number A, is it wrong because of indivisible?
Because of indivisible, we can, saying that it's indivisible, we cannot cut it up in smaller pieces. Yeah, an atom is broken into smaller pieces. They're called electrons, protons, and neutrons.
Right, just want to make sure.
Yes, that is the word that makes it false. Good call on that. Next one, letter D. Atoms of different elements can combine chemically to form compounds. Back in 1803, he said that statement. Is that statement still true or false to this day?
Oh, yeah.
Yeah, that's still true. I mean, y'all are doing pretty good. Now, letter E. Forgive me, I guess I did leave a little space, but I just didn't see it. Letter E. Atoms of one element, it says here, can not change into a new element during chemical reactions. For an example, long time ago, people were like, hey, let me get lead. That's the element for lead, the symbol Pb, lead. I know, Pb, lead. They were using Latin words, so that's where the symbol comes from. So it says here, long time ago, people were trying to get lead and turn it into gold. Yeah, Au is gold. Again, Latin words. So using the knowledge right now, 2025, Have you been able to find anybody or know of anybody who's able to change lead into gold?
No, not chemically, but
Mmm.
change it through, like, was it nuclear fission? Fusion?
Oh.
Fusion or fission?
Oh, well, either one. Either you're telling me I can go ahead and I can change these elements, or I can get these two elements and I can combine them together and make it into a new element? No, we haven't been able to. They will not stay together. They will crumble. Yeah, they won't stay together. We have not. We are good, but we are unable to make lead into gold or any other elements into a new element. We just haven't been able to. So that's true. He's right. We cannot change one element to form a whole new element. We can try to slam. We've got atom smashers machines in CERN, and Sweden. I try to think which country that was, Sweden, and they can smash protons, neutrons, and electrons together to try to make a new one, but they are unable to create this into gold. They will crumble. They just don't stay together. We haven't figured that part out. So at this moment, he's still true when it comes to that. So there's a little bit more reading here for you to do regarding John Dalton and just a little background history of it. All right. This is a picture of what he kind of believed and thought these elements were. If you were a gold element, for an example, you would just be like this little tiny gold sphere. And if you were, a lead, you might be this little dark silver sphere. And maybe a little bit bigger, a little bit smaller, but you're all the same. Unfortunately, it's not true. J.J. Thomas comes around in 1897. Doesn't take much longer. 1803 versus 1897. That's not much of a difference. But J.J. Thomas started to change by doing experiments and changed our idea of what we believe the atom to look like. Now, his experiment, which is a quiz/test question, is called the cathode ray tube. The cathode ray tube. So now we're starting to do experiments. And we're like, hey, there's these quote unquote atoms, but we don't really know much about them. Why? Because they're so tiny and we don't have the technology to look at an atom. Let me just get an atom, put it on a microscope. We can't put it on a regular microscope and just look at it. So they were figuring out, and J.J. Thomas comes around, he figures out this really cool experiment. He's called it the cathode ray tube experiment is what he did. So it says over here, just in case if you wanted to see, there's a picture of this famous little guy over there. All right? Yeah. It says to determine what he was doing was he was using his experiment, number one, to determine the mass of a single cathode ray particle. Okay? Well, what's a cathode ray particle? Let's keep going. He found it to be that a cathode ray particle is negative. A negative charge with mass less than a hydrogen atom. Okay. Well, they did know that if you're a hydrogen atom, you're a gas, and if you're a gold atom, you're a solid. So they knew a little bit about the atoms and elements on the periodic table. Somebody else at the same time that this was going on was getting the periodic table and starting to create it. Believe it or not, the periodic table was multiple different types of forms before we see it now today. They had one that was a periodic table that was a circle. And you would go into around to this circle, and then you would go up to the next circle. So they had different forms of the periodic table until the one that we have now today. He also discovered through his experiment, because of this negative, what do you know that's negative inside the atom? Already, you know it. Electrons. He discovered the electrons, which are also negative. So now let's pause for a moment before we go any further, because you're a pretty smart cookie and you already know some information. He uses this cathode ray, and this cathode ray, which so happens to be a negative charge, who he was able to be the person to discover the negative electrons. So if you had to imagine, he has this cathode ray, and this cathode ray is this invisible ray that's beaming, and it's going, and it's actually about to hit something. Okay, it's about to hit some elements. he figured out that we have these negative electrons. If this cathode ray, which is invisible rays, boom, it hits atoms which have these negative electrons, how did he know that they were negative? Because negative and negative does what?
Positive.
Not negative and negative do what? Not math. Repel each other. Math. Negative and negative makes a positive.
Oh, yeah.
So what he had was, here's a little bit of his experiment. So I'm going to just scroll over here real quick for a moment. So he has his cathode ray, which has a negative charge, and what happened was he noticed that there was some deflecting going on, and it would cause them to deflect or repel each other, because negative and negative do not attract, they repel, kind of like magnets. Yeah, so he believed that the atom was this big, he believed, positive charge blob with little negative electrons floating around it. He called this the plum pudding model. I mean, I guess if you're the one who discovers it, you get to call it whatever you want. So what he believed was, let me go ahead and find a different color. He believed, and I'm going to go with the light, with my pen lightly. So he believed, here's my pen, I'm going really lightly shading it. He believed that an atom was made of this positive charge blob, and inside of it was these negative charged particles that he's called electrons. And because his negative charge cathode ray, we knew that cathode rays at the time were negative. When a cathode ray would come over here and hit it, it passed straight through it.
So wait, were the electrons lines or the dots?
We're I'm putting just little lines as a negative line.
Okay, I'm just gonna, yeah.
Whatever you want to put, but he believed that it was a positive blob and that there was these negative like sprinkles all throughout of it, that these negative sprinkles were called electrons, and when his cathode ray would shoot, and if it hit it, it just kept going. But if it shot and hit the negative particles, now it would deflect, or I heard the word repel, because negative and negative do not want to attract, which is true. He called this a plum pudding model. So back in the late 1800s, a popular dessert was plum pudding. And so plum pudding dessert was a pudding blob, right? Imagine if you saw pudding like in a container, it's like this blobby thing, right? But there were sprinkles inside of it. And so they had like fruit sprinkled inside of this plum pudding. But those fruit would stay in there. Imagine if you have you ever gone to the grocery store and you see like Jell-O that has a fruit in it? And so it's kind of like a solid material, but yet you can shake the Jell-O around, right? You can shake that Jell-O. And inside there, that Jell-O, you've got like pieces of fruit. I don't know, what do we want to call it? Peaches? Peaches. These peaches are all inside of there. Those were negative charge particles. And so when he had his cathode ray, which is a negative charge, and it hit this negative, it would repel. And so in his mind, this is how he envisioned it through this plum pudding. It says here, though, which part of Dalton's theory did Dalton, regarding Thomas, did he disprove? One more time. Forgive me, I didn't say it good. Which part of Dalton's theory did Thomson disprove? So Dalton's up there. This is Thomson. He disproved. Let me go back. There's part A, B, C, D, or E. Which part did he disprove? Well, it can't be the T's because showing that.
Oh, A.
A.
Because it can be divided into negatives by electrons.
Right, absolutely. Absolutely. So he disproved part A. So because of his experiment, he disproved Dalton's part A theory, which Thomson found Found, found that the atom has these negative parts, and it's not just a solid, hard sphere like a BB ball, but it has parts to it. And so if I want my parts to attract, I've got to have obviously some type of positive and some type of negative. And that's where he figured out that all of this he thought was positive, and then there's these negative sprinkles throughout. And if it repelled, then there's some type of negative or positive and positive. But since he had a negative cathode ray, and there was some repelling or separation because they didn't want to attract, then there must be something that was negative, and there must be some positive particles in it. So it's not a solid sphere, it's parts. Okay, and here's his cathode ray. So let's keep going. Well, if that's the situation or the case that's going on, then Ernest Rutherford said, I'm going to do some experiments too. Because if there's some parts that are negative, then there's got to be some parts that are positive. And let me figure out a little bit more about this positive particles that must be inside the atom, he said. So he did an experiment, and his title or the name of his experiment is the gold foil experiment. Yeah, just like how it sounds. They didn't get creative on their names back in the 1900s. So he literally got gold, and since we know that gold is malleable because it's a metal, he sat there in a lab with a hammer and he smashed gold to keep it very, very thin. He smashed it. Have you ever seen tissue paper before? Like when you get present? Same thing?
Like gold leaf.
Kind of like gold leaf. Kind of gold leaf or like tissue paper. And he made gold into like a tissue paper, or if you ever seen gold leaf paper where it's super, super thin, that's what he did in his lab. So he got gold and he smashed it. Why did he use gold? Why did he use a metal? Well, because it's malleable and you can make it super thin. Obviously, he was trying to hold it up so that way he can do an experiment with the gold. Couldn't really hold up liquid, right? And if I wanted liquid, I would put it in a container. He was afraid that a container, like for an example, plastic, would interfere with his experiment. He needed something that was solid, that was going to, quote unquote, stand up. So he had his gold leaf paper, or like tissue paper made of gold, and he was holding it up with something. So now he has this gold that he knew was pure gold, number one, and it was an element on the periodic table. So I'm going to get this, and I'm going to smash it super thin. So it's called gold foil experiment. So he thought that what he did was there was these alpha particles would pass straight through the gold foil. Oops, that's an L, not a T. So he got alpha particles. Alpha, which is a positive particle, which we already knew. He already knew that. Alpha particles were positive. And he said, I'm going to pass these alpha particles through my gold foil, and let's see what happens. So he's found that some of the particles actually bounced back. Whoa. If my alpha particles, and we just talked about like magnets for an example, if my alpha particles bounced back, then my positive So with this, he was the person who discovered the proton. Rather than just assuming that there was this positive blob, now he proved that there was something that was positive in there because it bounced back, because positive and positive would repel.
How did he see the particles bouncing off?
Good call. Well, how in the world would he see this? Because if these rays are invisible. So here is his gold foil experiment. He got gold foil. See it? Here it is right here. Right? He had it standing up. Then he had this little screen, a fluorescent screen around it. So his alpha particles shot through the gold that was super thin. A tissue paper is pretty thin. That's how thin it was. And so every single time his alpha particles went through the gold foil, look, on the other side, that means that why would it go through the other side and hit?
Because it hit the area where the electrons were.
Well, it hit the area where there was nothing was. This proved that my atom had a lot of empty space because it was able to pass straight through and hit the other side. Why did it hit the other side? Because atoms are made of empty space. It didn't get stopped. But when this alpha particle hit the positive proton, it would bounce back and deflect because positive and positive would repel. So I was just showing that question that Daniel had. Let me go back. So he actually got credit for discovering the positive proton. And we just saw in that experiment, he concluded that atom was made of mostly empty space because it went straight through, which is true. We do know nowadays that atoms are mainly empty space. But he knew that it contained a tiny, dense, positively charged particle inside of it, which we are considering that, right, to be the nucleus. That nucleus or that center. So here is Ernest Rutherford's idea of what an atom looks like. We have these negative electrons, and in the center we have these positive protons that, and do you see how I didn't shade it in this time? And I didn't shade it in because he figured out that there was a lot of empty space. That's where it was passing through and hitting the other side. And every time it hit the screen, you would see a little spark, a spark, a spark. And he was able to see that, oh, well, if I have this gold sheet that I hammered super thin and my alpha particle is able to pass straight through it and not be affected, well, then that means that there must be some empty space. I mean, not like we can walk through walls or anything like that, but there's empty space. It passed straight through it and it sparked on the other side. But a few of them, like I said, did spark and deflect. And when it reflected or deflected back, you can see that's only because it hit the tiny little positive nucleus that has a positive charge. Now that proved that atoms now are definitely not these atomos that are these solid little spheres. Atoms, number one, have empty space. Atoms, number two, have a positive charge. And atoms, number three, have a negative charge. Oh, snap. New technology, we're figuring things out. But wait a minute, we get this new guy over here, James Chadwick. 1932, believe it or not, 1932 was not a long time ago. 1932. Okay, so James Chadwick comes along in around 1932-ish, which again is not a long time ago. And he said that there's a problem with Rutherford's model. The Rutherford's model couldn't account for the total mass of the atom. So they were now at this time doing experiments, and they figured out that, for an example, if you had gold and you took the mass of that gold, well, there's a problem. If I added up all the protons and added up all the electrons, where's the rest of the mass? The mass should be this. It should be this, but it was weighing less mathematically. This is what, when I put it on the scale, it weighed here. But when I counted it out on a piece of paper and did the math, I got this. There's a difference. Where is this mass coming from? What's going on? So James Chadwick said there was a problem going on with Rutherford's model that could not account for the total mass of the atom. It was always heavier than predicted. Well, that's because there's one more particle that we haven't discovered yet. And that's what he was thinking. There's something else inside of this atom that we haven't figured out yet. What the heck is it? He proposed, I agree, the existence of the neutron, which has a symbol of an N with a little zero at the top, meaning no charge, zero charge. He proposed the neutron. He says there's got to be something else that mathematically, when we do the math, it wasn't mathing out. My math wasn't mathing because I'm missing something. Okay, positive protons. Okay, negative electrons, he says, but there's got to be something else. Again, were they able to look it through a microscope and see the particle pieces? No, not at all. Again, a lot of this was theoretical that they were doing, and they really still didn't visually have their eyes on it yet. So it says here, there has to be this neutron that has a mass nearly the same amount as a proton. And he says it must be no charge, which is neutral. Why does he say that? Well, at this moment, all we know truly, which is true, we only know positive charges and negative charges. So if it didn't have this neutron didn't have a positive charge and didn't react with the alpha particles, and it doesn't have a negative charge with the cathode ray, well then, what the heck? It must have no charge, he says. And it's like this invisible particle. So he decided that now we have this nucleus in the center, and he says in the center we have our positive protons. He also believed that we have these neutral neutrons. And he said, you know what, I agree with you that, yeah, we have a lot of empty space, and we have these negative electrons that are floating around. But I believe, he said, that we have an atom that's a little bit more organized, not just like a blob of plum pudding, he says. He goes, no, he goes, I think there's a little bit more of an organization. And we've got our nucleus that contains positive protons, neutral neutrons. And if the neutron weighed the same mass as a positive proton, that would account for the total mass of an atom, which is completely true. It looks like he's right, but he's still very, very wrong, and we still do not even use that model. That model is junk to us nowadays. So here's a picture of Chadwick. Okay. Now let's go to Bohr. Oh, now we're getting somewhere. Bohr, he thought he was spiffy. Well, I'm going to tell you, for many years, in the early 1900s, we believed in Bohr's model. Bohr's model is junk also, to be truthful. Okay, but he got credit, I guess maybe for trying. I guess these scientists get credit for trying, right? Right? Yeah, you get it. Yeah, you for trying. It's like what do you call it? participation trophy.
Yeah.
Right? He's like,
Pity trophy.
Yeah. Here you go. Here's your participation trophy. You're completely wrong, but you still get to be famous. So,
He didn't do anything.
I can help a little bit.
I mean, you help with prove what's wrong.
Yeah, like
Why is he in here?
I don't know. Well, let's talk about why he's in here. That's good. It said number one, there was a problem. Since opposite charges, it says here, particles attract each other, why didn't the positive nucleus draw the negative electrons to it and suck and collapse an atom? So that's what he was thinking. I don't know. I guess he had time to sit around and think about stuff like this. One more time.
Yeah, he's a philosopher.
Right, I don't know, I don't have this kind of time, but he thought there's a problem, because if we go back to the other one, then why wouldn't the negative electrons, if you stop and think about it, that's a good question, doesn't suck into the positive proton and cause the atom to collapse? Ooh. Okay, number one. Number two, he also proposed that the electrons are arranged in 7 circular orbits. Or orbitals. Around the nucleus. So he proposed, let's go back. We've got the positive protons, we've got the neutral neutrons, we have the nucleus. He proposed that electrons arrange in a circular path around it in these orbitals. So this would be an electron and an electron. Then we would have the second orbital, which would contain electron, 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 2, 4, 6, 8. And then we would have another orbital, and we would have another orbital, and we would keep going. How many orbitals? It says it right there, 7 orbitals. And he believed, I mean, you can keep going, but I'm going to stop. But he believed that electrons actually are arranged in a certain way. Because if we just had the electrons, imagine if you just had a cereal bowl and you just poured it out the cereal. It's just going to fall into the bowl. He says there's no way that the electrons just fell into it, right? He says there's no way, because if that's the case, then they're going to attract to each other and my atom is going to collapse. He says no. He says, I believe that electrons are arranged in orbitals, 7 to be particular, and that these orbitals contain the electrons, and this is the reason why my atom does not collapse, because everybody is, do you see how we get more organized? Everybody's organized, and we are going to stay, you stay in your lane, 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 and you stay in your house.
Yeah, but that doesn't really explain why they're there.
Oh, we go into, it gets, that's next unit. That's next unit.
I mean, I know, well, I sort of know why, but
That's,
I
yeah.
haven't really learned it.
That's next unit. So that's what Bohr says. And he comes over here and says, we have these energies, and each electron lives in their orbital, and so we have what we call N1, N2, N3, N4, N5, N6, N7, these energy orbitals, and those electrons stay where they live. You stay where you live, I stay, the protons stay where I live. In my house, you stay in your house. In this situation, we're not going to attract and collapse an atom. We will stay as an actual formed substance, okay? We won't just upon each other. Okay, well, we're getting a little bit better. But again, though, to be honest, we don't even use that. He's completely wrong. Next unit, we'll talk more in detail about the actual orbitals of it a little bit later. But it says here, why was the electron discovered first? Stop and think about it.
Magnets pushing particles away.
No. No. Here we go. Thank you, say it again. Front line. And so why was the electron discovered first? It's the front. It's the front line. It was discovered first. You discovered the first thing first. Just like we discovered the closest thing in outer space to us is, what's the closest thing in outer space? The moon. We've been able to go to the moon and discover the moon. Did you just see last week that there's a 26, 27-year-old girl who decided to be one of the first people to go to Mars? She will not return back to Earth. This is a one-way trip. She committed to NASA.
Oh, shoot.
Like last week, she committed to NASA.
So I'm
Last
gonna
week.
eat.
She will not come back to Earth.
So she's dead?
No, she hasn't gone yet. But when they send her, it will be a one-way trip.
So she's gonna die?
Eventually, we all.
Everyone does.
Yeah, but there's
Everyone
nothing
dies.
funny.
No, I mean like,
Oh, we're starting stuff funny
You're
here.
gonna send me.
Hey, wait a minute.
I mean, she's
And
gonna die
Santa
there.
doesn't exist.
Oh,
man! I'm so sorry, Taj. But, well, hey, either there or in outer space. But she just, so you're right. When you're going to go and invade or go and discover something, you discover the outside first. That's the reason why the electrons were discovered first. They are the outermost. Oh, we just recorded you crying about Santa.
Oh, yeah, you're already
I don't care.
because they are located on the outside. I'm not gonna say anything else because I don't want to, say anything. We'll talk about the tooth fairy next time. Go.
Okay, the tooth fairy is real. I always get money. Tooth fairy is real.
Really? Even at this age?
So whenever she's going to Mars, we're trying to remember how long she can stay, like how long she
Yeah.
can live on Mars.
Her mission to Mars is she's going in the idea that she is going to land at Mars and be one of the first people to help colonate Mars. As in, for her to grow substances and like food, like her own
Try to
food.
create a life on Mars.
Correct. So that's why that's hopefully how she will be able to
So she's-
continue to
Bad
live.
idea.
She's
Is
gonna
there
grow.
air?
She's gonna grow a quarter pounder.
No, there is no air on Mars.
She's like interstellar.
Yeah, like interstellar, and only the people that grow quarter pounders are McDonald's.
I think that.
That's like $1 million quarter
Like,
pounder.
Todd, we do not have 3 hours to straighten you out right now.
Wait, how
Okay,
is she
but-
gonna grow? Wait, how is she gonna breathe? Like, how
They have plans like the ISS, like the
It's gonna be like a dome, or a building that they're gonna work on, kinda like Interstellar.
Oh, so kind of like some trees and stuff, just to keep the oxygen.
It might take a while to grow a tree, but yeah, let's, ooh, we're gonna keep going, Todd. We're gonna keep going. Why was the neutron discovered last?
because it's in the middle.
No,
No,
Cause it's the general.
no,
Cause it's the first one.
no,
Well,
It's
that's
the
not.
most, it's the most like.
because it's neutrally charged.
because it's neutrally charged and it's
Right.
almost invisible to it. Because it's a neutral charge, because it has no charge. That's why it has no charge. It has that neutral charge, no charge. Nobody was able to figure it out. Alrighty, turn the page. So, almost done with the notes. It says here, we've got a recap. A recap that I put into a little thing over here for you chart. It says particles. Why is this not straight? Particles. We've got the electron, we have the positive proton, and we have the neutral neutron. You can see that that's how we write them out. E negative, E positive, and N with a 0 for no charge. Who discovered it? Oh, because I promise you quiz day is coming around. Thomson, Rutherford, and Chadwick. Wick. It's located on the outside. It's located in the inside nucleus. It's located in the inside of the nucleus. The charge is a negative charge, positive charge, and no charge at all. It was like invisible, like a ghost. And the symbol like I said earlier, instead of me writing out all the words, I'm so sorry, I just did the symbol. Electron, positive proton, and a neutron and end with a 0. So relative mass, we are going to have a little bit of math later on when it comes to this, but our relative mass, honestly, we consider the mass of an electron 0, nothing. Those electrons are almost weightless.
Wait, zero, that's not a zero,
That's, for me, that's a 0. I don't know, for me
Just-
personally.
Okay.
Me-
That was like a no solution.
Oh, okay. Well, this,
All right, bro, this is not math.
okay, there you go. Because it's not math class, I have no clue what no solution means.
Bro,
Not here. And relative mass, we consider protons to be 1 and neutrons to be 1. They are equal. They are a 1-to-1 ratio. Okay? A 1-to-1 ratio. But the actual mass, because yes, electrons do have actual mass. It is 9.11 times 10 to the negative, because we know what exponents are now, 34th kilogram. Darn right it is, and that's why we write it in scientific notations. The proton and the neutron mass, look over here, relatively they are 1-to-1, meaning actually they are also going to be the same to each other. 1.67 times 10 to the negative 27 kilograms. So that must also be the same for the neutron. And at this moment, we have not discovered anything different about this. That is true.
6, 7. Great job, number 6.
No, negative 27 power.
Okay. Any more questions?
Whoa. Let's keep going, though, for a little bit so that way we can get through this a little bit more. It says here, as a recap, in general, we say that inside the nucleus, it's composed of not only protons, but it's also composed of neutrons. As a recap, overall, though, in general, that inside of the nucleus, because that's what we're talking about right now, we're talking about the inside of the nucleus, overall has a positive charge because the neutron has no charge. And we also say that all of that is composed inside of the nucleus, meaning that the nucleus is very dense, and 99.97% of an atom's mass is located inside the nucleus. That an atom is mainly made of empty space. Now, outside of that atom, outside of the nucleus, 99.9% of it is just empty space where the electrons travel and live. We will talk about that next year, how they travel and where they live at.
Alright, that's the whole.
That's a whole other thing that it just blew my mind about 5 years ago when I finally figured something else out about that. It literally is a lot. Overall, the outside of the nucleus has a negative charge. And then it says here, how does that fit together? Electrons are held within the atom due to their attraction to the nucleus. They want to be, yes, attracted to the nucleus, but those neutrons actually act like pillows, and they're neutral, they're like a buffer zone. And they, thank goodness, help buffer the electrons from completely collapsing the atom together. Now, too many neutrons can actually make this atom or an atom radioactive. Okay? We do have radioactive elements in our periodic table.
Wouldn't you figure more protons make it? Wait, no, actually, never mind. That was silly. I stalled myself.
And since all atoms are, we consider, oh, this is a highlight moment. This is a highlighter moment. My highlighter, thank you. My highlighter sucks. Let me see, how about this?
Do you want to use my fancy highlighter?
No, I'm gonna go with this.
Yeah.
You got it from Tom.
That is not vintage.
Oh, it's like a
You're
little pen.
fancy.
Well, I got
Y'all
the best.
both have this?
I got the best
Where'd
highlight.
you get it from?
Tuning center downstairs.
Oh.
You'll see it.
Okay, I'm gonna have to go.
All my highlighters is secret.
You got one? Okay. So I went with a banana, orange, yellow school bus. It says here, since all atoms are considered electrically neutral, in chemistry, one more time, in chemistry, you will always consider all atoms to be electrically neutral, but all atoms will eventually become charged elements, or charged atoms, sorry. One more time. In chemistry, we consider all atoms to be electrically neutral. I can't say this enough and stress this enough for later on future units. One more time. All atoms are considered to be electrically neutral, but we know that all atoms eventually becomes an ion or a charged element or charged atom, except for everybody in group 8 or 18. They will always stay electrically neutral.
So eventually becomes ions or what's the other?
Charged particles. And that's because the proton number always equals the electron number. That's a huge important information. Why are they considered electrically neutral? Because the positive protons equal the negative electrons.
What is with nuclear fission? Can you change that?
Well, they change it on their own when they become ions. All right, other than that, I've got a little bit more time. I'm trying to see what else we got. Let's finish this page at least. Let's do that, and then then you can start the rest of your Monday. The Bohr model. Remember how I told you the Bohr model is really not the model that we use, but Bohr model is super important. We use it when we're talking about just doing free drawings of atoms that are going to combine and stuff. Even though deep down inside of my brain, I know that that is not correct, we still use his Bohr model. So yeah, he got credit. Yeah, he's not correct, but we still consider his model to be important in chemistry class. It says here, we've got positive protons and we've got neutral neutrons that are located inside the nucleus. Write the number of protons and neutrons inside of the nucleus with using those symbols, the P and the N. Just give me a moment. It'll make sense in a moment. Number of protons equals the atomic number. Okay, whoa, that is another highlighting moment. I'm just going to box it in then. Students forget this all the time. And when you're doing your math, it's like, what do you mean you don't know it? The number of protons in an atom is always the same number as the atomic number. Meaning that if I have a periodic table and I look at the atomic number on a periodic table, that number is the proton number. Here we go. When looking at my periodic table, the number that's at the top is the atomic number. That atomic number always tells me, let's look at it, the proton number. But wait a minute, I'm going to draw a little arrow. Boom! Somebody's mathing over here. That row is on fire. Let me say it one more time. For an example, lithium. Lithium has an atomic number of 3. That means that number 3 is always going to be the proton number. But because all atoms are considered to be electrically neutral, then that means that lithium also has 3 negative electrons. Do you not see how amazing a periodic table is becoming now? So let's keep going. It says here the mass number. Okay, this is going to be a little bit of math. The mass number is the proton number plus the neutron number added together. Whoa, comma. So you find the neutron. How do you find the neutron? So to find the neutron, you should do the electrons. I don't even like that. You should do the mass number, subtract the atomic number, so you can get your answers. one more time. My mass for my atom is going to be my proton number and the neutron number together. So what I'm doing is I need to figure out, well, how many do I have? To figure out how many I have, I go ahead and get my mass number, take away my atomic number. Give me a moment, and hopefully it'll make more sense.
I
And
get
just
it. Wait, that would mean beryllium has 5 neutrons. Very left. That's right, left, top, next to hydrogen.
beryllium.
Wouldn't that mean it has 5 neutrons?
So in this situation, it has 5 neutrons. I got the number 9, take away 4, and 4 is not only the proton number, it's the electron number. My neutron number is getting the mass number, subtracted from the atomic number, gives me my neutron number.
That means, wouldn't it be able to attract another electron?
Oh, we'll have to get to that later, but yeah.
Yeah.
Okay, so absolutely correct. It says here one more time, as a reminder, because this is super important, atoms are electrically neutral, that's what we highlighted up here, meaning they have the same number of electrons as well as the same number of positive protons. Now I will leave you alone. You have a